Okay, thank you everyone. My name is Wen Liang, and I'm a research scientist at Meta Reality Labs. And our organization is the Applied Research Org, supporting all the Meta's application in the domain of AR, VR, related to human perception and reconstruction. Today I'm going to talk about some completed work and ongoing work for real-time 2D human perception for AR and XR at Meta. Here's the agenda for this talk. First, for those who are not familiar with AR, VR, I'm going to provide a background. And next, I'm going to introduce some typical devices and applications for 2D AR XR at Meta. Then next, I'm going to give a deep dive of technology stack. I'm going to discuss data, CVML, and on-device rendering. And finally, I'm going to take some short time to discuss AR fitness in terms of AR, VR domain. So first, I'm going to give a brief introduction of AR technology. When we talk about augmented reality, usually we mean we are using computer-generated perception information to enhance some signal we get from real world. As illustrated on the left, you can see the virtual content is overlaid with authentic words. And by doing this, the user can get richer information. And when we talk about mixed virtual reality, it usually means a simulated experience user can get from a VR headset. And typically, the applications are VR gaming and immersive 3D visualization. Then talking about mixed reality. When we talk about mixed reality, it usually means physical and digital objects coexist together, and sometimes these objects can interact with each other. As shown on the image in the left, the background is a VR gaming scenario, but the user can see their own hand in the scene. And even more, this hand can interact with some object in the scene, which create a lot more and entertaining. In this slide, I'm going to define the scope of this talk, because the title says it's 2D, so definitely there's no 3D key points and mesh shape estimation, which are some other ongoing work we will show later in the future. And when we do 2D application, typically we focus on a single RGB sensor, which is useful. And because it's real-time AR, VR XR application, so we need to require our technology to be served on device at a frame rate of 20 to 30, which means for one frame, the latency is 30 to 50 milliseconds. And we are not only target on high-end devices. Instead, we are targeting to a variety of different devices. This is a very big constraint, adding a lot of challenges, because typically we see for low-end devices, the latency could be 2x to 5x slower than high-end. This slide shows some typical application and devices for AR and XR at Meta. On the left, these are Instagram and Messenger. They are all mobile apps, and we support mobile AR features mainly for AR entertainment. And in the middle, these are Portal and Messenger desktop device. And for these two devices, we mainly target on two scenarios. One is video meeting, and another is family social. And we've built a lot of AR features on top of these two devices. And on the right is the Oculus VR headset. And you can see there are cameras on top of the VR headset. So using this camera, we can capture the authentic world. And by merging the authentic capture into the VR world, we can form some mixed reality features. This diagram depicts the general workflow. I'm using an AR application as an example. It's a general workflow for a typical ML model development cycle. On top of that, you can see first we need to have an annotation platform. And we have both vendor data and user-generated data injected into this platform. And after the data is annotated, we will inject the data into a privacy-aware data warehouse. And then when the data is ready, we can start some model training. At Meta, we mainly use PyTorch for deep learning model training. And we developed other framework and tools on top of PyTorch to support CV-specific model training. These are Detection2 and Detection2 Go. We will dive into deeper later. After model is trained, we need an inference engine to support on-device model inference. And at Meta, we use PyTorch Edge. I think externally it's also called PyTorch Mobile. And to use this framework to support on-device inference. And currently, this framework can already support not only CPU inference, also GPU, and for some high-end iOS devices, it also supports neural engine inference, supposed to be much faster. And the last module is AR delivery. It in charge of like final rendering of the AR effect on your device. And there are two components. One is Spark Engine, which is a main backend responsible for end-to-end system inference to collect the signal and render the effect. And we also have Spark Studio to expose to third-party users, creators. These creators can use this tooling to design whatever AR effect they want. Let's zoom in a little bit to the data system. Talking about privacy, as I mentioned just now, our data has both user-generated data and non-user-generated data. And this data has two types. One is image, and another is video frame. For image, we typically get this image from Verb image pool, Instagram, Facebook. And for video frames, we will sample the frames from vendor-collected videos. To determine which data we want to have human annotation, typically we can, at the beginning, we can use random sampling. But whenever the first model is trained, we will evaluate the model and find there was some drawback or limitation on certain dimension of the current model. To further iterate, we need to use active learning to find specific data which can cover those dimensions which model are performing badly. Then talking about annotation too, in the past we rely on more vendors' annotation platform, but now we already have a centralized internal annotation platform called Halo at Meta. But beyond that, we actually largely rely on another technology, is auto-labeling. It's not human annotation, but instead we rely on machine-generated data. And all this data are stored eventually in privacy-aware data storage. Here are some stats of the PyTorch framework. As I mentioned, more than 90% of the model at Meta now is trained on PyTorch, and this counts for around 4,000 models trained on PyTorch. And within these 4,000, about 1,700 of the model are actively used in production. And I believe this is just a statistic for Facebook Meta internally, but in recent years, I believe more and more teams and companies are adapting PyTorch framework as their deep learning training tool because it's very easy to use. And here is a demo for the Detection2 and Detection2 Go I mentioned. Both frameworks are open sourced. Here's a link you can check for more details. And Detection2 is originally designed for instance detection and extend to other CV tasks. And Detection2 Go is built on top of Detection2, which dedicatedly for on-device and real-time model training. And you can see these two frameworks now support different tasks. This is instant detection, pose estimation, dense pose, and also instance segmentation. Actually, there are many more applications which are ongoing work we are working, and in the future we will share more information. After we get the training infra, then the next question is how can we design an efficient neural network? As I mentioned just now, the latency budget for real-time application is very limited. Typically for a model inference for one frame, we only get 10 to 20 milliseconds for core model inference. Then how to design this architecture? We cannot just manually design because there are like infinity number of possible combination. It's hard to exhaust. So the potential solution is neural architecture search. At Meta, we designed a framework called EpiNet. It's a device-aware differentiable NAS technology. That means we through the NAS search, we can get a model not only optimized for number of operations or accuracy, but also the on-device latency. It can be a NAS result targeted to certain device. And some key feature here as illustrated in this diagram. At the beginning, we need to have some fundamental design block. And we put this design block on device for latency benchmarking to understand the latency for each block. At the same time, we also use this fundamental block to build a supernet for the NAS search training. And eventually, after training, during training, we also consider both accuracy and on-device latency as a network cost function. Then after the eventual optimization, we can get a model optimized on both accuracy and on-device latency. Here are some results from version 3 of this framework. And as you can see from the plots, our framework right now can achieve state-of-the-art on ImageNet and can performing other like popular, efficient neural networks. Next session, I'm going to talk about data efficient learning. The motivation here is to train the ML model, we need to use a huge volume of data, millions of image, or sometimes even video. To collect this data or annotate this data is very costly. So there must be some strategy for data efficient learning to utilize our budget better. We focus on this topic a lot. So there are several topics. First is synthetic data. Here is an example of 2D body key points synthetic data. As you can see, you can see how realistic it is. And the key challenging here is we must make sure the simulated human and environment and pose and action to be realistic enough to fill the gap between real and synthetic data. And next approach is about machine labeling. The idea is simple. We train the high capacity model in background and use this high capacity model to do the prediction on a larger volume of unlabeled data. And use this unlabeled data with machine label to train our eventual model. Because everything of the annotation happens offline, so we don't need to care about the latency here. In practice, we find this method is very efficient for our model training. Another topic related to machine labeling is semi-supervised learning. And this diagram depicts the workflow of semi-supervised learning. First, we need to have we need to train a supervised learning model, use all the labeled data, and we make a two copy of this model, one teacher model and another student model. Then we use pseudo labeling from teacher model to use as ground truth of a student model to train student model. Then we also iteratively refine teacher model and student model together. Eventually, we will get a model utilizing both unlabeled data and labeled data and achieve a better result comparing to the initial model trained on labeled data. And we have a paper published in 2021 about this approach. The last one about data efficient learning is the strategy, how we search the image from the web content. Because the web content has billions of images, so how to search the image, what required, which satisfy our scenario is important. So the approach is like this. First, we need to have a large-scale representation learning model. And at Meta, we are using so-called class fit model, which published in 2021. And after this model train, we can get more than 150K clusters. Then when we start the image searching, we will put several seed image into this cluster to generate embedding of the seed image, then do a simulatory search among the clusters to find several top clusters close to our seed image. Then eventually we sample image from those top clusters to generate the image content search result. After data efficient learning, I'm going to highlight several model improvements in the past years we've done. The first one is about robust padding. Everyone may be familiar with when we build a neural network in the convolution layer. Sometimes we need to do padding, and if you don't do anything, the default option is zero padding. And our researchers find if you don't set any special method, then the default zero padding usually is uneven padding. Then it will introduce some artifacts. And these artifacts will propagate through layers. Eventually, in final result, you can see some strip-like artifacts in the result. And the solution suggested from the researcher is to do some symmetric and smart padding. And here is an example of a segmentation result. On the left is the original baseline model without any specific padding. Then on the right is the one corrected using the smart padding. And the next thing is about spatial temporal robustness. Through the development of AR and Mixar technology, we found there are two things affect the user experience a lot. One is the boundary quality of your model prediction. Another is temporal jitter of your model prediction. So we put a lot of efforts to improve these two dimensions. Here are two examples. You can see on the left the prediction and at the boundary is very low quality compared to the right, which is an improved model using some specific trick to improve boundary quality. And on the right is an example of 2D key points. You can see at the beginning there was a lot of jitter, and after we add some post-processing filter, the jitter is removed significantly. After modeling, I'm going to talk about on-device rendering. This diagram depicts the life cycle when a model is trained, then finally it's generated on-device inference-ready model. So the step is like this. First, after model training, we need to do a quantization. Means we need to convert the model from AP32 format to int8. And here, this example is for post-training quantization. And in many times, actually, we also do quantization aware of training, which means after model training, the model width is already int8 format. And after this step, we need to convert the model from PyTorch format to a TorchScript format, which is more generic for different devices. And there is another step for further optimization for this TorchScript model. Typically, there are two main modules. One is memory optimization. Another is computational graph optimization. Then after these optimizations, we can eventually sieve this model into light interpreter format. And this is ready for on-device inference. Then the last module is Spark Engine and Studio. I already described Spark Engine is end-to-end responsible for the whole system end-to-end to deliver the signal and the AR effect rendering. Studio is for the AR creators. Here are some demos. There are a lot of applications support in Spark Studio. I cannot exhaust all, but you can see you can get a taste the underlying technology we are using. For example, face tracking, body tracking, hand tracking, and skin segmentation are all used for these AR effects. Here are some ongoing work we are working on, haven't shipped. The first video is about a girl is dancing, then character is on her body, and when she's dancing, the character is waving with the body. Next one is some symbol flashing in a 3D domain, and the girl have some shadow on her body. The last one is about expression transfer. We have a model to transfer the neutral expression to a smiling expression. And here is an example of a mixed reality. The player is now playing a Beat Saber in VR. And outside of VR, we have another camera to capture this player in authentic world. Then we have some SLAM technology to put this player into VR video to form some mixed reality experiences. This feature right now is in production. And in the end, I'm going to talk about some AR fairness evaluation example. I'm going to use a segmentation model as an example. AR fairness is very important at Meta. We want to make sure our model is performing equally on different dimensions. Typically, after the model is trained, we need to collect more than 1,000 videos, and we need to annotate video frames within these videos. Then we need to define more than 30 categories for AI fairness. Within these 30 categories, we define more than 100 classes. For example, for skin tone, we have 3 classes. We use the Fitzpatrick skin scale for the definition. And in the plots, you can see actually the model is performing fairly equal on different gender category classes and skin tone classes. This bar chart is like exaggerated, but if you read the metric value itself, you can see how close these metrics between each other. That's all I have today. Thank you, everyone. Before I get to Q&A, I want to see our organization, XR People, is hiring. If you are interested, please feel free to reach out.
Nice job. Nice job. Hey, yeah, we have time for Q&A, but before that, I have a question for you. If you go to slide number 18, I appreciate you number your slide.
Not so familiar with this.
Yes, so here, at some point you mentioned you crawl the web to get the content to search. Are you using the same images for modeling as well? And is that legal?
Yes, that's legal. As I said, I think I got advice I cannot release more details, but what I can say is all the user-generated content used at Meta to train the model is follow special privacy compliance.
Right. So because most of the time, we don't see any watermark or anything on the image that it is copyrighted. If you do the Google search, you see underneath of the image says that may be subjected to the copyright. And how do you collect those which are not subjected to the copyright?
Oh yes, we are not search from the external web. We are using image from Instagram and Facebook.
All right.
And there are certain consent form between us and users. Okay. And definitely yeah, I guess I cannot really raise more details.
All right.
Some suggestion from legal.
It's going to be a question on top of my head forever. All right, so we have time, 5 minutes to ask your questions. Any? Thank you for your presentation, by the way.
Thank you.
Thank you so much for your great presentation. What 3D annotation tool do you use, and is there any open source 3D annotation, especially for 3D segmentation, exists that Facebook offers?
I'm not aware of any tooling is open source, but that's a good suggestion. I can deliver this message to the tooling team.
Thank you.
Yeah, next question. Tim, can you pass the mic?
And the relationship between the teacher and student that you make, can you make that a network by itself where it branches within context? Meaning that you have a human and then you have branches from that and you subtrain it to multiple things. It's not only 2 levels. It's a branching tree of understanding within certain contexts, so it keeps on branching. For example, if you say silver, right? So it's detecting a silver color, but many things could be silver color or could be silver as in something else. So it's actually able to understand context within annotation as well.
Sorry, I didn't fully understand.
It's okay. So can you make multiple teacher-student that connect to each other and they are a relationship R1, R2, R3? So the student is a teacher for something else.
I think it's interesting. I'm not expert in this field. I think some potential gain from this maybe is robustness. Multiple students can play as regularization, right? For example, you can see similar idea for some sorry, I forgot the terminology. Using some. I can chat with you offline. I think it can be considered as an extra regularization to prevent the network to be overfitted for this idea. But I'm not expert.
Okay. Thank you.
Next question.
Hey, you talked about FPNet, the differential aware NAS architecture. Is that publicly available?
Yes, it's published in ICRR, or if I remember, yeah.
And what hardware platform will it work on?
I'm not sure the NAS2 is open sourced. Yeah, I need to check with the author. I know they are working hardly to make this platform more mature.
Got it.
But that's a good idea. If it will get open source, it will be in Detection 2 Go. Sorry.
Okay. And you said it's already open sourced, or is it?
No, the training framework is open source. It's called Detection 2 and Detection 2 Go. But for NAS, I'm not sure it's open source.
Ah, okay. Got it. Thank you.
Yeah, we have time for one more question. Here. Mike's coming.
Is there any tool which you use for drawing the bounding boxes?
Draw the bounding box. I think for annotation platforms, they should have this tooling.
And it's not open source?
Yes, it's not, yeah.
Okay, thank you.
All right, so with that, thank you so very much.
Thank you.